Okay, what's up? It's Amplifier live stream repair time. So if you want to catch my live streams, if you want to know when I'm live, and so you can jump on, ask me questions, probably troll the hell out of me, and just get involved with a pre-recorded but live Q&A amplifier repair, hit my subscribe button and hit the little bell next to the subscribe button, and you'll be emailed and you'll get a push notification on your phone every time that I go live. So you can be like, holy shit, Beveridge is live, let's get on this thing. Fucking start trolling me and asking me all sorts of questions like, guy, what will happen if I put a ferry on my output section? No. What's the most common question I get? The most common question I get is probably what power supplies I use. Power supplies, these are Dell server power supplies. They are 2100 watt models. I don't know the model number off the top of my head. It's some flipping long chain of numbers and letters. But yeah, if you search eBay or any Google Dell 2100 watt server power supply, these will be the ones. They have 3 fans, one big one at the back, 2 at the front, and they can output 175 amps at 12 volts each. So I have 2 in parallel, and they parallel beautifully. So I've got 350 amps worth of load at 12 volts. They actually are underrated. They can put out a hell of a lot more than that before they moan at you or before they die. I have had one of these die on me actually. I was benching a Lanzar 7K at 0.5 ohm off of just these. I was like, I don't want to. I was like, fuck it, try it. Fucking yeah. One of them blew a lot of the transistors inside, and I used some IRFB 3077s from a Banda amplifier. In fact, from a Banda power supply in the power supply here, and it worked perfectly fine. I checked all the specifications, they seem to be marry up nicely, so I was like, okay, put these in, blah, blah, blah. Nightmare to repair though, nightmare to take apart, but yeah, anyway, so while we're talking about power supply, Banda repair, let's get cracking with this. Okay, welcome guys. Today we're going to be looking at something a little bit different. I have done videos on Brazilian amplifier boards before, but I have not done a video yet on a Banda amplifier. I have repaired many of these Bandas before, but I've never just done a video on it. Actually, out of all of the Brazilian brands, it's probably a close tie between this and Taramps for the number that I've repaired before. So this amplifier is a Banda Viking7001 or 7001. So this claims to do 7,000 watts RMS into 12 volts, and it should do about 9,000 watts RMS into 14.4 volts. You're probably thinking, how the hell is this flimsy ass thing? Just to compare size, right? This board here, this is a JBL GTO 14001. So this is rated for 1,500 watts at 2 ohms, and that's 9,000 watts at 1 ohm. What the hell? Now let me just explain a little bit as to why this amplifier is rated so high and why it actually does do the power that it claims it does. So in an amplifier you have the 2 sections. You have the power supply section and the output section. So normally for an amplifier of this size, the power supply section will be absolutely huge. You'll have loads and loads of capacitors on the power supply section, which will charge as soon as you put the battery in, and then you'll have loads of 064N FETs, usually these big ones, especially in a 9K amplifier, loads and loads of these, all being driven by separate banks, and they will then power the output section. This amplifier doesn't use lots of the big 064N FETs, it uses lots and lots of more modern FETs. These ones are the IRFB 3077. And these FETs are a lot newer than the old 064N. And as time goes on, MOSFET technology gets much better, and MOSFETs can be driven easier, they do more power, they are more, they have a lower resistance between the drain and source, which means they can do a bit more power. These are just much better FETs. And each individual's FET's power rating is very high, and we have got we've got 18 of them here. So 18 of these will be able to provide sufficient power to do 9,000 watts RMS. And these are driven also by ICs instead of buffer transistors. So you've got 4427 buffer ICs. They're basically the same as the buffer transistors, but they're in an IC and they have 2 channels. So very simple power supply section. And the next thing you're wondering is probably, where the hell is all the transformers? Usually you see loads of parallel transformers in these amplifiers. Well, this, most of the big amplifiers that you see, 9000 watts and the 14001 here, this uses two voltage rails. So it will use a high voltage rail and a negative voltage rail. So for example, plus and minus 80 volts. There's a lot more involved in generating the two different waves, rails. In this amplifier, it's literally one positive rail that swings up to, from memory, it's like around 180 volts or something. And the difference is with these amplifiers as well, everything is pushed very close to its limit. So the power supply FETs will probably run very close to their power limit. The capacitors here, they are 200 volt rated. They'll be run relatively close to their limits. The output FETs here, 90 and 20D, they'll be run very hard and close to their limit, which is why these Brazilian amplifiers are not that stable at loads under 1 ohm, because everything's already run quite close to its limit at 1 ohm. And the Korean amplifiers are built with a bit more headroom, if you like, so that's why that they can be run a bit better at these low impedances. But saying that, the size difference is still immense. So the power supply section here, it is big enough to supply 9000 watts. These are your filter caps. Nowhere near as many as on a Korean board, but it's not needed because the switch frequency is incredibly high. These amplifiers are controlled by a PIC, so that's a programmable IC, and that will control all of the protection circuit and the switching frequency for the output section, power supply section, etc. How the amplifier turns on, it'll go through a check state first, so to make sure everything's okay before it powers on. And the switch frequency is a lot higher with these amplifiers. The output section uses 8 90N20D MOSFETs, and this does 9000 watts. To put this into perspective, the tar amps equivalent of this amplifier has half the number of output FETs. So the tar amps will still do apparently the power with only 4 90N20Ds or equivalent. They use some a different FET as well, but very similar in power ratings. Now these MOSFETs are very modern MOSFET technology. They're bloody expensive, and they can do a ton of power. They're rated at stupid main camera battery has died and I forgot to charge up the spare battery, so you're on this one for the time being while that charges. Yeah, they do a ton of power. They're rated for 90 amps per FET. That is their theoretical current limit, and provided they can dissipate the heat quick enough to the heatsink, they will do that. So 8 of these should be more than sufficient with enough headroom to do 9000 watts at 1 ohm from this board. And Banda, which is different to tar amps don't filter the output. So obviously you know from my previous videos, when you look at the output from these MOSFETs, you have the output switching frequency, which is the very high frequency square wave you see, which is what generates the audio signal. Tar amps don't filter that out. That gets sent straight to the speaker terminals, and the idea is that your subwoofer's voice coil acts like an inductor and filters it out, which will generate a little bit of heat in the voice coil even on idle, which is not ideal. But it kind of, I get the thinking, it kind of works, I guess. But the Banda, no, they actually put dedicated inductors to filter out the high frequency switch before being sent to the speaker terminals. And that's also why on the tar amps you can't use the Termlab Magnum power probe, and you can't use Fluke wireless current sensors, because they get really confused by the high frequency switch on the speaker. So let's go over this amplifier and the repair procedure and see what's wrong with it and how to repair these. They are a simple-ish repair, however, they can be an absolute headache and they don't like being repaired. So although the repair is relatively simple, there's not a lot of components on this board, really, that die. They can be an absolute headache, and if something dies that is not common, where it takes out more of the board than usual, the usual just FETs and driver, things can get a bit of a headache, and you end up just blindly replacing parts until you find the thing that is causing the amplifier to die. Also, I've had in the past with these amplifiers, because it uses such little output FETs, if there is an issue with the drive, even running the amplifier on a very low current supply, if there's an issue with the output drive, there is enough energy stored in these 4 rail capacitors to kill one or more of the output FETs if there is an issue when you're powering it up on a low current supply, which is very, very annoying, because if you have an intermittent problem, you power the amplifier up and if it's fine, and then suddenly one of the FETs will die and you're on a low current supply. There's no working out why it's done that. The wave looks good. I have one of these boards sitting in the donor pile that works perfectly fine until you remove the remote. As soon as you remove the remote wire or turn the remote wire off, it kills two FETs. It's almost like when you remove it, it dumps all the cap to two of the FETs, and I can't figure out why. I've replaced pretty much everything that I can think of. So I came up with an idea. Whilst we repair these, to ensure that we don't kill any of these expensive FETs, because these are like £3 or £4 each if you don't know where to get them from, what we're going to do is we're actually going to remove these rail caps. Okay, and the reason for that is we should be able to power the amplifier up without having to charge the rail caps and without there being any current to dump into the FETs if there's a problem. What we will do is we won't run the amplifier without caps at all, because that is a stupid idea because there's no filtering. What we will do, however, is we'll replace these 4 caps just temporarily with one single cap that is a much lower farad rating, but with the same voltage rating. So these are 200 volt and these are 1000 UF. So we'll replace that with a 200 volt, I don't know, maybe 500 UF or even a 1 UF should do enough filtering just to get this up and running on the bench. And that way, if there is a problem with the output section, rather than the caps draining through and killing some FETs, hopefully the FET will be beefy enough to survive the single lower rated cap rather than all 4 in parallel. So, in order to diagnose the issue with these amplifiers, the first thing, it's the same as any other Korean amplifier. You want to take your multimeter, put it on diode beep setting. It's for continuity, and it also shows up ohms at a low ohm reading. And you want to go through each of the output FETs and see if any of them have shorted. So let's have a look. We start with the first one, go between pins legs 1 and 3 first. Okay, that looks alright, and we'll get different numbers by switching the legs around. And now let's go between 1 and 2. Or 2 and 3, sorry, looking at backwards. Okay, so we have a dead short, and that dead short is on the rail. So that's we've got the gate here, and then between this is the rail and ground. So we have a dead short there. So this FET is potentially dead, but because the gate is still showing its correct value, it's probably not this one. Go to the next one here. We have the same short on the rail, which is as we'd expect. But this one is showing a 129 resistance on the gate, so this FET's probably dead. Same short on the rail. And we have a 116 ohm, so this FET's possibly dead as well. Same short on the rail. And that's a correct gate value, because I've worked on so many of these amplifiers. So these 2 are likely the dead ones. These amplifiers work in banks of 4. You have these 2 running on this driver, this 2 this driver, this 2 this driver, and this 2 this driver. So you have 4 banks, 4 driver ICs, 1 high, 1 low. So the fact that these 2 have died means that we need to replace all 4 of these and these 2 drivers. However, because these amplifiers are so fussy, and because we have literally 2 banks that are running the same output here, what I'm going to do for all these amplifiers, all these bandas that I'm going to repair, I am going to replace all 8 FETs for the same brand new batch even, sorry. And that should ensure a reliable repair going forward and minimise any issues as a result of unbalanced FETs, because they're so flippin' fussy. So I will use brand new FETs in all of these amplifiers, whether even if 1 FET has just died, or 2 or 4, I'll just replace all 8 of them, and I'll replace any driver ICs that are on dead banks. The same thing goes for checking the power supply in these. So these power supplies on these bandas are so strong, and the protection circuit is so quick, I've never seen one die. Even amplifiers with destroyed output sections, the power supply never ever dies. So we just check. On the power supply we only really have to check 1 FET, and that is the capacitors charging. So we have no issue on the power supply side, and you can usually confirm that by just taking your probes and measuring between positive and ground. And if you have the capacitors charging like this, where the number increases, then you usually have no dead power supply section. Alright, first things first then, we need to remove all of these output FETs. Very easy. Now, these boards are not the best of board quality, and by that I mean that there is more chance that you risk damaging the pads if you apply heat for too long, or you screw up with the iron. So what we want to do for these is take our solder sucker, get our iron heated up, oh goodness me, I don't know if the camera can make that out, but this is the gain knob on these amplifiers. It's really small and really shitty, and by the looks of it they usually get destroyed. So that gain knob there has been mutilated by the wrong size screwdriver, someone forcing it to try and turn it up. So I don't know, we might have to replace that or something. I have got some spares of these boards. I might have to get some spares of these gain knobs, because that is not looking pretty. So So apply new solder to each of the legs. One of these legs will be very hard to remove, and the reason for that is because it is on the ground, which is the whole back of the board. So if you think about this board, this whole bit of board here is one thick ground trace, and that has a very high thermal mass. So when you apply some heat to this pin, the heat will just dissipate through the whole board, through the ground path, and it makes it very hard to remove. So what we're going to do is, rather than sucking the solder from that, which is going to be nearly impossible, we're going to suck the solder from the first two, the gate and the output, and then what we're going to do is we're going to heat the ground one and wiggle it out whilst it's being heated. That should be a lot easier. Yeah, there's quite a lot of thermal mass on these boards, and so desoldering these FETs is not the easiest task, I have to admit. Okay, so let's just make sure that our first two pins are nice and wobbly there, that we've sucked all the solder out of the holes. So just give it a push from the other side, get it off the via. There we go. Okay, so our first two pins are wobbly in the hole. So what we need to do then is, I'm just going to take a rag because this FET's really hot now where I've been heating it. I'm going to heat the third ground leg, give it a gentle wiggle because we don't want to pull the via. Okay, wiggle it until it's very loose, and then just slowly and gently start to pull it out, and it will come out of the holes like so. Completely intact, with no pulled vias, no pulled gate traces. So that FET is ready to go, and this one probably survived. So with all these ones that I'm removing, so obviously I'm going to replace all 8 FETs. All these ones I'm removing, I'll build up obviously a inventory of these ones with the same batch, so I can drop those into other amplifiers in the future. So same again, we're going to pull the solder, suck the solder from these first two, because these come out nice and easy. Push the legs away from the edges of the vias so that they don't pull the vias out. There we go, nice and wobbly, you see. And then heat the third one. And now the whole thing is wobbling, and just gently pull it out. Not much force needed at all. There we go. So now the output FETs are out, I'm going to do what I said about removing the capacitors, but what I'm actually going to do is leave one in. So I'm going to remove 3 of them and leave one in. That should reduce the ramp up, the startup time from the small supply enough that it doesn't take ages to turn on as usual, and also reduce the current available if there is an issue on the output section, but still supply enough filtering for the power supply. So we're just going to use the same method here. We want to reuse these caps, of course, so just going to heat up all of the capacitor legs here, and hopefully there's not a huge amount of thermal mass on the board. I can get these out relatively easily. Might actually be a case of heating this and then bending pulling the capacitor from the other side of the board to pull the leg out. You can do that as long as you don't pull too far, and you can just walk it out slowly. So you just do one at a time, one leg at a time, one way then the other, one way then the other. There's a huge amount of thermal mass on this section because this is the ground pin and the whole board is ground, the whole rest of the board is ground. This process of walking it out reminds me of an old bass song I used to play back in the day in the bedroom. Oh, who's it by? Can't actually remember. Now walk it out. Hey! Walk it out. That had a very high bass line that suited my 8s nicely. Because they were not tuned, they were not designed to play very low, those things. Not the box, just the drivers, the kick mid-bass drivers really. FS up at like 60 Hz or something. There we go, and eventually we have walked it out. Hey! Ah, shit! Okay, so there was a bit more thermal mass on there than I envisioned, so that's what you want to try and avoid. So you see that? You see how we have pulled the via? That's not ideal. It's not the end of the world, because we don't technically need the via on the top. All it is it's just a, if we have a look on there, if we have a look at the via here, we don't technically need that because there's nothing happening on the top of the board. So all the voltage, all the signal, all the power comes in on the bottom of the board here, and it goes across the cap here. So this via on the top of the board is not necessary, it's not required to hold the cap in place really, or to connect any power to it. It's just a little annoying. So I shall leave the soldering iron on for longer next time on the next cap to hopefully avoid that. I'm going to turn the heat up on the iron as well to about 420. 420! So we're turning the iron up to 420 because we want to blaze that solder. Blaze it. I'll leave this on here and let the heat soak into the board nicely so that we don't pull the via. Because ain't nobody likes to pull the via. Not me. Hey! There we go, so that one I heated up, and the additional heat there up to 420 on the iron has helped that a lot with coming out smoother. So that was pulling out much nicer, much easier. So this one we shouldn't pull the via. Come on. That's it. Getting wobbly. Where are we on the camera? Getting wobbly. You can hear it with the creaking there. So you just want to do it a little bit at a time. You don't want to put a lot of pressure. You want to walk it out in baby steps. I could probably get away with sucking the solder actually now, but because these holes are so big, even if I suck the solder, there might be a little bridge of solder left on that will just pull the via out, and I don't want that. I do not want that to happen. There it is. Now, did we pull a via? Ah, fuck! We still pulled a via! How? Oh no, we didn't. No, we didn't pull a via. No, we didn't. False alarm, we didn't pull a via. There was a square of solder left on the leg in the shape of the via. That was obviously the solder which is on top of the via, but if we turn the board over, we should see that, yeah, look, where are we? Yeah, look, we didn't pull the via, so pull via, no pull via. Good. Okay, fantastic. So we have removed 4 capacitors there, 3 capacitors there, sorry, and all the output FETs. So what we want to do now is power the board up. So the outputs which died were on this side. So we had 2 here that were dead. So we really want to go ahead replacing these 2 drivers. But what I want to do is I would like to power the board up to show you the drive waves on the screen for these, so you can potentially see a dead drive wave in action, so you know what to look for if you're looking for dead drive waves on this type of board. And also because I think this is going to be the first time that I've actually powered one of these boards up without any FETs in. So yeah, that should be pretty cool. I would like to see how it behaves and what the waves should look like without any FETs in. Now, these boards, the ground here for the power is actually bolted to the case. So when you take the board out of the case, there's no way of holding the ground block on. You see this here? So what we're going to have to do is just temporarily, while we're working on it, is solder the ground wire here to the board, just so that it's not falling off. And now see, I don't actually want to solder it to the top there, because then that will leave a nasty blob of solder, and then this block won't sit down correctly when we put it back on. So I am going to solder it to, we're going to solder it over here to the edge, because it's the same place, and that is much easier to get rid of once we're finished. Cool. Yeah, ground. So let's get our scope all hooked up and get our scope camera going. So the scope probe always on the main ground most of the time with 99% of amplifiers. Only occasionally do you need to put it on the RCA ring ground. So with these amplifiers, I don't yet know whether they need the FETs in to oscillate, whether they're self-oscillating, or whether we'll get a drive wave on the gates, especially of the low side, without the FETs actually in, because I've never done this before without the FETs in with these amplifiers. So we'll see. If we need a sine wave going into the RCAs, no worries. We'll just hook up a frequency generator and do that. Also making sure we've got no solder bridges from our soldering on these pads. They're quite far away, so we probably haven't, but it's definitely worth checking every single time you finish soldering before you apply any power. Check for solder bridges, because they can cause more damage than was there before. So let's probe the cap here. So what I want to do is get that there, and actually first of all let's probe the power supply. So you can see we've got 9 volts there, so we apply a little bit of power, and that comes on super fast compared to when it was 4 capacitors. This would take about 5 minutes to power it properly, so that is a great idea. I'm very glad I took those capacitors out. So let's just change the scope settings quickly to reject low frequency and noise rejection off. Okay, cool. So amplifier is operational. Now what voltage do we have on the caps here? So we've got 123 volts DC on this side of the cap, and that's ground. Okie dokie. So rail voltage is present, that's fine. So now let's check to see whether we have anything on any of these gates. So we have half rail voltage on each of these. Okay, cool, and we do have some drive. So that looks like, is that high side or so that is down at 0 volts. So that's probably going to be, that's a low side drive, because I think the reference there is 0 volts, and that's a high side. Okay, so we do have low side and high side drive present on these amplifiers. What I'm going to do is put the coupling to AC so we can zoom in on this wave. Now this is pulsing, which I haven't seen before from any other amplifiers. So let's see. That looks nice. That is a pulsing wave. That's a pulsing high side. If all the high sides do that, then I would imagine that is not an issue. The other high side does that as well. That's the low side. Now let's go over to the other side of the board where we had the blown FET. So that is the low side. Let's check the high side. Does that look the same, or does that look more bouncy to you? No, that does look the same. Okay, so that driver's potentially okay. And that is a low side. And that is a high side. What I'm going to do is I'm actually just going to stop it on that up wave. I'm just going to compare it to one over here. Oops, wrong one. Yeah, they look pretty much the same. So on this amplifier, we may have a situation where the drivers on the side that blew, they survived because the drive waves, everything looks completely equal throughout the board. Oh, you've honestly no idea how much nicer this is with just the one cap in. Look at this, right? So this is a really, really big amplifier. So with 9 volts, 4 amps worth of input power from the mains, from the charger, we're going to probe the main rail voltage here, and it takes 2 bumps to get it up to full rail. And then when we let go of the remote, it sinks down very, very quickly, within a few seconds, and then the amplifier is safe to work on again. Fantastic. That is very, very, very good. So I've got 6 or 7 of these amplifiers to work on. The Banda Viking7001 and Banda Viking8000. They're the same board. The only difference is I think they increased the transformer windings a little bit to have a little bit higher rail voltage, and then they used better caps, so slightly higher rated voltage caps, etc. So because I've got so many and I want to do a full refresh on every single one of them, I ordered an absolute bulk load of 90N20D FETs, and this cost me a flippin' bob. This costs a lot of money. This look how many. Oh shit! I just turned my the static on the bag turned my light off. Okay, so yeah, this is a 50. I think it is, no, almost 50. I think it's 48 90N20D FETs. And yeah, if you know how expensive these are, this is a lot of money. So what we're going to do is, I'm curious to test the specifications of this batch that we got. Hopefully they're all the same batch. So we've got FTCU batch in all of these. And hopefully we'll have all exactly the same FTCU. Yes, we do. Thank you very much. Same batch. I like it. It's a good day for me. So what batch do we have on here? Something completely different. Very, very different. So, okay. What we're going to do is we're going to take our cheap Amazon transistor tester, which I highly recommend. For £20 these can be had, and they tell you all sorts of things, from measuring transistors to inductance to what time your dinner's going to be ready. Let's measure first of all some of these 90N20Ds that didn't die, some of the ones from the good side, because that will tell us a lot about how the amplifier was running and what sort of power. Comparing it to these new ones, we can see what difference it will make with the amplifier. So let's just make sure none of these were the shorted ones that I pulled out. Okay, no, that one's good. So we're going to measure this one first. From memory, these 90N20D FETs, the specifications between the same batch can vary quite a bit, especially with the RDS. Now, RDS is a number that you want to be as low as possible, because that is the resistance between the drain and source, and the drain and source is where the power is on the FET. So the lower the resistance on the drain and source, technically the more power that the FET can dissipate before it gets too hot. The higher the RDS, the hotter the FET will get at the same power. So let's hit the tester and let's see. I'm just going to go through what all these numbers on the tester mean, because they're very important when you're checking FETs. VT, this is the voltage which the FET will turn on. So the gate of the FET is obviously the switch that turns the FET on and off, and that has a threshold voltage at which point the FET will turn on past a certain voltage. So this is telling me that the VT, the turn on voltage, is 4.6 volts. So this FET needs 4.6 volts in order to turn on. The CG is the capacitance of the FET on the gate. So because this gate is a switch, it has a very small capacitance, and it acts a bit like a small capacitor in the fact that it will retain some current after the gate signal has disappeared, and it will take a very small amount of time to charge as well. So the gate capacitance is very important when you are designing a circuit to drive this FET. 9.75, that's a relatively high gate capacitance. You'll find that with these bigger FETs that do more power, the gate capacitance generally is quite high, which means that you need to take this into consideration when you're designing a drive circuit to offset that capacitance, because that can cause issues with the drive circuit. The last number, which keeps disappearing on here, is also incredibly important, and that is the RDS, the resistance between drain and source. When the FET is turned on, how much resistance is between the drain and source where the power is going to be made. 1.7 ohms in this case, which is okay, it's acceptable. It's a little bit high for what I like, but it's acceptable. So this FET came from the batch from factory 305P. So let's have a look at another 305P and see whether we have similar results on the tester. Make sure this one wasn't a dead one. Okay, so we have a VT of 4.7, CG of 9.8, which is the same, but the RDS is 2.4 ohms, which is quite a bit higher than the last one. Not a huge amount, but this FET will get hotter doing the same power than the other one did. We also need to take into account a little bit of test lead resistance. So these are shitty test leads, and they probably induce some resistance into this test across the drain and source, which is not ideal. But we can see the difference, even if it's not necessarily accurate to the 0.1 of an ohm. We can see which FETs have a higher RDS and which ones have a lower. See, it's jumping around a little bit, went to 2.6 now. So this FET definitely has a higher RDS than the other one. So if we were choosing the best FETs to put in our amplifier, this one would probably go to the side as not as ideal. Let's do a third one just as the last one of these old FETs. And what I'll probably do is I'll probably bag them up with separate RDS ratings, and I can use them in different amplifiers to that effect. So third one here, last one we're going to check from the old batch. So again, VT is exactly the same, pretty much 0.1 volt different, which is it could just be the tester. 9.53, which is the same, but the RDS was a bit lower here with a 1.3 ohm. So this is a whole ohm lower than that other FET that we just tested, which means that this one will do a bit more power and stay a bit cooler. It won't get quite as hot doing the same power. It surprises me, to be honest, how much variance there is in RDS of the same batch. So obviously these are the FETs that came from the factory in Brazil, and we don't know for sure their legitimacy. They could be, I mean, I don't know, they are printed pretty differently. They have pretty different prints, so they're obviously made in different places, and they have lots of different codes and everything like that. They're not the same etching. So what I'm going to do is I wonder whether the FETs that they use are manufactured in a slightly cheaper way to maybe these ones that I've got as a replacement. So hopefully these ones that I've got a replacement are a bit more consistent with their readings. Let's see. This is one of the new ones. Now that's a bit more like it. So 4.5 and the CG is about the same, but the RDS is 0.8 ohms. That's much better. I like that. That is much better. I like to see a low RDS. So fingers crossed that's not just a one-off, and hopefully all of these FETs are actually a nice low RDS, and they should run cooler and be less prone to dying. Look at that. Yeah, much better. 0.7 on the RDS. So, I wonder whether these Banda amplifiers are as unreliable as they are because wherever Banda are getting their 90N20 defects from in Brazil is a bit of a shit factory. Look at that, 0.8 again, so that's very, very consistent. Very, very consistent. I'm going to do one more of these new ones. Again, 0.8. So our new FETs have a consistent RDS across the board. With the FETs that were used in factory from Banda. This is another one that I haven't tested yet from the original batch from the Banda factory. Just to make sure, I can't believe what I'm seeing right now. What? What? Are you kidding me? 7.8 ohms? That's got to be an error for sure. That's got to be an error for sure. That must be tested. That. No way. 6.4. Okay, it's a bit lower. I'm just going to reseat these test leads because okay, so I don't trust these test leads that much, but I don't think we should be seeing a value as high as that. Either way. It's going down. It is going down. Okay. So is this just a meter issue? Because I can't believe that this has an RDS of like above 3 ohms. That would just be stupid. So the drain and source is 2 and 3 here. .2. Every time I test it is going down. Not that time. Just in case it is a weird tester issue, let's put one of the new ones in. And if this reads 0.8 again, and the other one is still all over the place, then I'm just going to put it down to these FETs that Banda use are shit. Yeah, 0.7. It's consistent. So it's not a tester issue. Put this one back. I think these FETs they use are just fucking terrible. 5.3. So it seems to have fallen and fluctuated around 5.3. And that, my friends, is no good. So whether that got damaged or not by the amplifier blowing, I don't know. I doubt it, because I don't think it would still show up as a FET on my tester if it got damaged. It would just show up as a bunch of resistances or diodes. But that is very, very surprising. I'm going to test another one from the amplifier. 3.7, that's really high. Holy shit. So on the amplifier, the effects that came from the amp, we've got a variety of 1.3, 1.7, 3.4, 5.2 and whatever else. I can't bother to test the rest of them. So, okay. Wow, okay. So potentially these amplifiers are so unreliable because the RDS is all over the fucking place. So you'll have, the amplifier will obviously be being used, and the effect with the highest RDS will die first and pull, maybe it's the one next to it, the high side or low side, down along with it. Wow. Okay. In that case, what I'm gonna do is I'm not going to change the driver just yet, because I'm curious to see if those drivers survived. We've got a very low current supply. We've only got one capacitor on there, so I think we'll be safe. Oh shit! You know, there goes my camera. Even if there is still a drive issue, it should show up before any damage is caused to these new FETs. So what I'm going to do now is drop them in, all these nice equal RDS FETs. You have no idea how happy this makes me. This is OCD, this is therapeutic right here. All the same batch, all the same RDS, all the same VT. Now this is a good parallel bank. This is nice matching. This is nice FET matching. Good FET matching. So we're going to put these all back in like this. And they don't cut the legs of the leads on these. They literally, they're just the right length as they are. So I'm going to solder these back in. Let's remove our power supply first. That would be a good idea. And let's drain the power supply caps. You want to see a spark, my friend? Bosh! Some fireworks for you. You know something funny, when I was first doing amplifier repairs about a year ago and I was working on these Bandas, I actually noticed the difference in RDS way back then. But I wasn't as knowledgeable on the FETs and necessarily what the different ratings meant. I just saw that they were fluctuating all over the place. I didn't necessarily realise at that point that that was to do with how much power it can dissipate compared to heat. So I emailed Banda and I said to them, all these FETs that I've taken from this amplifier on a working bank that didn't die on the other side, I've checked all of them and I've checked them from many different amplifiers and the RDS is all over the place. So what you're seeing today isn't just this amplifier. I've been seeing this variety of RDS readings from Banda amplifiers, the FETs that they use, for over a year now. I emailed them and I said, why is this? I don't think they're being matched properly in the factory. And their reply was, the RDS can be changed by as much as touching the FET, the static on your fingers and things like that can change the RDS all over the place. It just doesn't necessarily mean that they're not the same. It's just what happens when they're being tested. And I accepted that. I was like, okay, that makes sense. That does make sense. No worries. I wasn't as knowledgeable back then. But now I come to think of it. Now I know a little bit more. I'm no expert. I have never done any training courses. I've never done any classes. I've never got any degrees. I've literally just been repairing amplifiers in my little workshop for a year and going by experience that I see. Everything that I know is from experience that I see. And from experience that I see, these RDS values shouldn't fluctuate like they do. So I think that Mr. Banda was telling porcupines and... So yeah, just a quick one in the chat. Aged Wizard, so with he says what difference to the amp these FETs make? Will it run a bit cooler or a bit more power? Having a lower RDS FETs in the amplifier will allow them to run a lot cooler. So if you think that resistance is the thing that generates heat, that's how light bulbs generate heat, that's how hair dryers and heaters and anything that has a resistance, when you pass a current through it, it will generate heat. And the higher the resistance, the more heat it will generate for a certain power. So if the FET RDS is low, then what that means is, that the resistance in the FET is low, RDS, resistance to drain and source, which means that the FET won't get as hot as a FET that has a higher RDS doing the same power. So with the Banda, with the FETs that this one was using, some of them having an RDS over 3 or 5 ohms, they will not like doing a lot of power and they'll get hot quite quickly. With the FETs that we put in, having an RDS down at 0.7, 0.8 ohms on the tester, it might be lower in real life due to the test lead resistance. The amplifier should be a lot more happy doing big power and taking sudden bursts of power, and it will run probably quite a bit cooler as well. I don't know, I mean, you guys tell me. So I've never done a course in MOSFETs. Can the RDS reading be changed that much from 0.7, where it looks like it should be, up to 7 or 5 ohms just from touching it, or just from different molecules in the air? Is that a thing? Because from every single other FET, not just 90N20Ds, 24N40Fs, 064Ns, every single other FET and amplifier that I work with, the RDS is pretty consistent, even in the FETs that come off the board that haven't died. The only FETs that I've seen with this crazy fluctuating RDS are the 90N20Ds that come with the Bandas, and actually I saw it a couple of times on some definitely fraudulent FETs that I got from eBay. So some fake FETs that you get, usually the ones that are discontinued, and a factory in China will be churning out these random FETs, or maybe they'll have like a massive overstock of like one type of FET, and what they do is they laser scribe a completely different model number onto the FET, which is more desirable and more expensive, so they can sell them off at a higher price and just hope that nothing comes back. Or maybe they were ones that didn't pass maybe the ones that didn't pass the integrity checks and their values were too far off to be sold normally. Maybe some other company will just buy all of their rejects and mark them up differently and sell them on in the hope that, you know, no one really notices. But I sure as hell noticed. I bought some 4.4. What did I buy? What did I buy? I bought some replacements for 640Ns that were supposed to be better. Here's what I bought, and don't buy these from eBay. I bought some IRF 4227s from eBay, from China, for very, very cheap, like stupidly cheap. And the casing looks completely different to any other cases that I've seen. The laser engraving looks different. It doesn't look as high quality, and when I tested them on the transistor tester, the values were all over the place. The VT was all over the place, the RDS was all over the place. And so the only FETs that I've ever seen where these values are all over the place are FETs that are not legitimate and are fraudulent. So I wonder whether Banda are cheaping out on these 90N20s and they're not actually 90N20Ds, or they're just really poor quality ones. And that's why we're having so many reliability issues with these amplifiers. But to be honest, I'm not going to bother trying to go to Banda and trying to explain this. I obviously brought it to their attention once before. They either didn't realise that this was a problem, they've made up some bullshit, or are just blatantly lying about it. So, I don't know. It's a real shame because the Banda amplifier circuit design is fantastic. It's a very, very good circuit design. Whoever they employed to design these boards knew their stuff. They have used the right number of FETs, they've used a good number of FETs. It should be very, very reliable. The power supply section is reliable as hell. I've never seen one blow. The output section should be the same. And I reckon it probably would be a whole lot more reliable if this is the case, and if the FETs are not legitimate, if they're really cheap and they've cheaped out. It's a real shame if that is the case, because it really puts a whole downer on the brand and makes people not want to buy it. So yeah, just quick, how the hell do you say that? They say your name, Emeritus E in the chat. These FETs that the Banda came with from factory are all the same. They're all the same batch from factory. They all have the same date codes on them. So yeah, they're the same batch, same date codes, but the RDS is all over the place. Like at this point in time, with these FETs that I was seeing, you know, I'm having to say, guys, don't buy these. I wouldn't recommend you buy these amplifiers at the moment, because I don't trust where they're getting their FETs from. It just seems a bit all over the place. I do wonder whether there's any other FETs other than the 90N20Ds that would work in here. I haven't really done a lot of searching. They would have to have this very similar total gate charge and input capacitance ratings, because we don't want to have to modify the drive circuit too much, because that just becomes a headache. Alright, so they're all soldered in nicely, and we've had a little chat about FETs. So what we're going to do now is reapply that power and hope and pray nothing goes bang, which shouldn't do. And we're going to measure the drive waves on these FETs, and we're also going to check that they don't get hot. Okay, so time to test this then. They've cooled down a bit, and finally got some charge in my main camera battery. I think the sound is a lot better through this condenser mic. What do you think? I'd like your opinions. What sounds better, the mic on my condenser or the mic on the cheap JVC camera that I was using a moment ago? So we're just going to take our temperature camera here as well, our infrared camera, and just to make sure that nothing gets very hot very quickly, when we apply the power here. And we're going to hit start on our scope camera. It's probably not in focus, but it doesn't really matter. So, okay, apply some power, and let's see what happens. Okay, I let it switch just for a small fraction of a second then, because what I want to do is I want to check the drive waves on this side. Also want to check nothing got hot. So you saw there that we had full rail voltage very, very quickly, which is great. So let's go over to this side and let's check the drive wave on this FET here, which is on one of the banks that did die before. Okay, that's a good looking wave. So now let's do the same and check the drive wave on the other side, on the other FET. Okay, so that is the low side drive. So what I'm going to do is, that looks pretty nice actually. That looks pretty good. So that driver definitely survived. Let's do the same and let's check the low side drive on this other one over here. We're out of view on this camera. Apologies. We're doing this side now. Yeah, that looks pretty good. The amp's not drawing any current either, because if it was, the power supply would turn off. I'm just checking with the infrared camera here that nothing's getting hot, which is not. The FETs are staying dead stone cold. So I think this amplifier is a success. A simple refresh of all the output FETs and it's working hunky-dory again. What we will do is we will do a stress test. I can't bench test this amplifier to full power because I don't have a big enough power supply yet. I would need a power supply capable of delivering about 12,000 watts, which is ridiculous. You know, I'd need like a huge bank of batteries and like more power supplies than I've currently got, and hook up my ultra capacitors, which I can do. It's just not something I've got around to doing yet. So we can do a stress test to a high power. We can probably do a continuous 4 or 5,000 watts RMS, but I can't get 9k out of it with the current supply. Let's just make sure that, so if we look at the board here on my thermal imaging camera, the main bits which are getting warm are parts of the drive circuit and the regulation circuit. So we've got some small ICs on here which deal with the 5 watt regulation and also generating the PWM switch frequency, and they are getting, the hottest they're getting is 26-27 degrees. It just looks hot on the screen because everything else around it is flipping 12 degrees on the bench, or we got 18 degrees over there, 15 degrees over there. So yeah, that's a high contrast on the screen. So yeah, the amplifier's been on for a fair bit now. Let's wait for the rail voltage to fall back down, which is very quickly on this amplifier because we've only got one capacitor. And we're just going to check for heat on all these FETs with our hand just to make for sure. Okay, so I think they all just get a little warm on idle, which would be normal for these because this is such a little number of FETs for the amount of voltage which is going into here and the amount of potential power that this amplifier can do. So I would expect these to just have a very, very faint warmth on them on idle. Let's just do a last bit of checking with all of these. So okay, let's just check. All the high side drive waves look the same. So I'm going to pause on the scope, go to the next one, unpause, pause, go to the next one. Oops, that's there. Let's just check that looks good. Pause, unpause, that looks exactly the same. So we're looking for waves that look absolutely identical across the board. So we're going to put the shield on my probe so we don't accidentally ground anything. Let's do the drive wave now, the low side drive. So that's here. So we're going to pause that one, go to the next low side drive, which is here. That looks exactly identical. Go to the next low side drive, which I think, is it this one? Yep, that looks exactly identical. And the next low side drive, which is, oh, that one looks a little bit wobbly. That one looks a little bit wobbly. Let's zoom in there a little bit. Let's zoom in a little bit there. Let's pause that and go back to this one. Okay, no, it's not vastly different. Slight difference in the driver there, perhaps. As long as it's not getting hot, we're good. Yeah, it looks the same when we zoom out. So I'm happy with that. Let's just check for heat once more. They're all just getting a lukewarm, which is what I'd expect. The temperature on these, just for your own reference, is 20 degrees. So it feels warmish to my hand because my hands are freezing because it's cold in this workshop at the moment. So my fingers that I'm feeling this with are 18 degrees. See, I've got 18 degrees on my fingers, 18.9. So it feels warm to my hands because they're warmer than my hands, but it's not hot at all. So now we just need to fit these caps back on and reassemble and do some endurance testing. Now putting these banders back together, and this actually goes for any car audio amplifier that screws into the heatsink like this. You might wonder why I don't use a electric screwdriver or power screwdriver, and the reason for that is it's very easy. This aluminium is like soft as cheese. It's very easy to cross thread and mess up the screw holes that you're going into. So when screwing these things back up, if you mess up the screw hole, it's a nightmare because it's difficult to get the clamp to push hard against the FET again, against the heatsink, which it needs to for good thermal transfer. So when you're putting this in, I always use a hand screwdriver and rest it against the hole first, screw it back a couple of times until you feel the thread jump on its thread, so you feel it jump down like that, and then go to screw it a little bit, and it should just screw really freely, like no effort required, until it gets to the tightening point, and then you can apply your torque. If you find that as you're screwing it down, so let's say we get this one here, let's put this in like this, jump it back a couple, and then go to screw it down. So right now I feel resistance instantly, straight away there's resistance there. If I could continue to screw that, and I'd be tapping a thread that's slightly off center to the original thread, and what that does, it weakens the aluminium thread that this tap has made, and it weakens it so that when this is undone and done up again, you risk actually losing the thread. So just pull it back out, find a new position, find a new angle, and try again. And now it's moving freely. So now we just do it there and tighten. Okay, so we're going to power her up first on the smaller 12 volt power supply with a load attached, and just see if we can play a little bit of music just to make sure that there is signal there and that it doesn't cut out or blow when there is a load attached. So let's get the power supply, and the load is connected, so let's fire her up, and we should see the two waves on the screen. If I put both AC and DC on, sorry, both channels 1 and 2 on here, then we should see them fall apart as the thing comes apart. Yeah, there we go. So we have on 1, let's do 50 volts, and tell you what, let's put 1 at minus 50. That way they should stay, what's it, no sorry, minus 100. That way they should stay about the same equal place apart as they move up. Okay, operational or no? You see it did actually fall down a bit there. Let's just make sure there's no DC offset so we can put our hand on the cone and feel. Make sure. Okay, let's power it up one more time. I always hate this bit. I hate applying a load. It's always a scary part. Okay, so let's hit the tune very quietly to start with. Just see whether this power supply will actually power it or not. There we go. So it's only a very, very low signal. Both waves look quite good. Both waves look equal and both waves look good. Okay, so let's shut that off, and now we're ready to apply the big power supply and make this thing move like crazy. So let's turn the dells on, and we're not going to drive this too hard because I don't want any low voltage issues to kill the amplifier. I'm sure it won't, but we're not going to be able to drive it to its full power, and also with this this speaker being free air, it's not going to take that much power to get to full excursion anyway. So okay, let's find our gain in there. Tiny little gain knobs in these, the absolute nightmare. And let's hit the power. This track is called Enter the Dragon by Le Lion. Very nice track. Ah, yeah! Okay, so another reason that, as you can probably hear, I'm using this woofer is it has a offset coil, so this needs tweaking a little bit. Yeah, this was actually a build that a friend of mine put together, this subwoofer. So this is a DD9912, but the soft parts here, or the hard parts, the carbon cone and all the coil and all that, was actually from a DDZ412, so the Z motor with the 4-inch coil. But this was removed from the motor, and we had a spare 99 motor laying around, so he loaded that up. However, it's very, very, very hard to get the coil lined up central without using the shims, without going through the dust cap. So, hey, we got Henry on the live stream, on the live chat. What's going on, buddy? Hope you're good, man. Cheers for tuning in on that. As a result, it is ever so slightly off center. You can hear around this side it's closer to the pole piece, and around this side it's further away. And as a result, we have a little bit of coil rub on excursion, so we just need to sort that out. But in the meantime, I use this as my amplifier testing woofer, because if the amplifier dies and chucks out full rail voltage to the speaker, first of all, this is an incredibly stiff spider, and second, it's a big coil, so it'll eat up the power, it'll eat up the burst from the amplifier's fault, and it won't shoot the cone into the stars. So we've been doing a bit more testing with this on a static and reactive load, and for that test I hook up a static load to apply a decent load to the amplifier because the impedance rise will be very high through air, and we add a reactive load so that the amplifier has an actual cone and coil configuration to push, because there's some EMF and some back EMF, so we need to make sure that it's happy playing that. So we run a 45-minute endurance test to quite high output power. On this amplifier it's actually quite close, well, not too high, but it was getting hanging onto the power supply's power limits there. Now it's quite expensive doing a 45-minute endurance test like that with an amplifier this big. Think of your electricity bill. But has to be done, obviously, and it's why these amplifier repairs are more expensive the more high up you go. It's, a lot of the cost is actually in the endurance testing to make sure that it works. I do offer a reduced price with no endurance test, however there's a very limited warranty on those. So yeah. So this passed with flying colours, and it's just very lukewarm to the touch. It doesn't feel like it's been driven hard. It's not hot, but you can tell that it's been driven. It's kind of like got that nice warm kind of feeling to it. Not hot to the touch and not cold either. Just like it's been used nicely, and it's like, yeah, I done some power. I did some work, bitches. Like, so this is all happy, ready to go back off to the customer. Bing! Also, just a couple of last things. We did replace the gain knob. That's all good. That's fixed because that looked horrific. And also, I wanted to explain why I didn't decide to change the drivers in this amplifier, and this is why. So for the possibility of the driver to be damaged, we need to have had the gate, which is what the driver is connected to, short or have high voltage shoved down the other way against what it's trying to drive to blow the driver up. Now in this case, the two legs that shorted were actually the drain and source, so the two here. So what will have happened when the drain and source shorted? All of the power in the rail capacitors will have gone poof through these two MOSFETs that blew the drain and source, because that then would have been a nice easy path for the electricity from the rail capacitors to discharge down. So they would have gone poof right from rail voltage right down to zero. So there wouldn't have been any voltage that would have gone through the gate to the driver, because that was a much higher resistance path. If we have a check from the resistance between the gate and the middle pin here, that is 133 ohms. And well, we also have a 133 because these are shorter, so we got a 133 ohms from the gate. So as far as the gate is concerned, the gate will have, for a very fraction of a second, these protection circuits are incredibly fast. The second that this shorted and dumped the rail caps, it would have gone straight into protection. So for a very small fraction of a second, the driver will have been trying to drive a 133 ohm plus the 22 ohm gate resistor, so 133, 43, 53, so 155 ohms. So the driver will have been trying to drive a 155 ohm resistance, or 155 ohm load, which for the amount of time that it had to drive that is perfectly fine. There should be no reason that the driver should die with 155 ohm load for the very small amount of time that this actually presented that load to the driver whilst it was turned on. So the drivers, they read fine, they looked fine on the scope. We applied the new FETs and they worked fine, and we've done 45 minutes worth of endurance testing, and yeah, so you know, this amplifier is about as good as we're going to get. I actually believe that this amplifier in its current state, because we replaced the FETs with the ones with the constant RDS, this should be far better than it was new and far more reliable. So I would say that we aren't going to see this one back anytime soon, unless the customer does some funky stuff when they're wiring, which customers do tend to do. So yeah, this one was quite an easy one. In effect, all we had to do was replace all 8 FETs, which most people with a soldering iron would be able to do. But it's all about checking to make sure that that is all we need to do. So it's easy to replace all the FETs, but it's not necessarily easy to know what you need to check and what things should be reading to make sure that that is actually all you needed to do. I've actually got about 5 more of these band amplifiers, the 7000 and the 8000. So I mean, a lot of them have just died randomly, and so I believe that is probably to do with the fluctuating RDS on these crap FETs that they've used. So hopefully one of those will be a little bit more in depth, and I can show you replacing the driver and what other parts around the drive circuit that need checking. Hopefully for you, unhopefully for me, because I don't like complicated repairs. Keep it nice and simple. It's good business for me. But yeah, catch me on another live stream where I will be doing another Banda, and we'll see if they're all the same or if any of them are a lot harder to repair. Yeah!